Hi, so this is a handout which is not from the workbook. I want to explain the difference between conservative and non-conservative forces with some visuals. And I will also explain why it is important because when we apply the energy conservation, um, we had the energy terms on left side, right? Delta K, delta U, and delta I. And we had the heat and work done on the right side. So starting with the weight force, we said that when we apply energy conservation and there's a change in elevation, that means there is really work done by the weight force. It's non-zero. But you can either do that, so you can either keep the work term by the weight force non-zero and on the right side, or you can ignore it. So that means you're gonna say the work done by weight force is gonna be taken to be zero, although it is not zero, but in the energy conservation it will be if you choose to keep delta U term, which is the gravitational potential energy on the left side. Okay, so you had two choices and you need to choose one or the other. You have to have one if there is a change in elevation, and but you cannot keep both of them at the same time because that would be double counting. It would be wrong. So the main reason that we could do that, because the weight force is a conservative force. So the gravity is a conservative force. Okay. That means if a force is conservative, it can be associated with a potential energy. Okay. So that's what we need to understand here. So this is the example here for the conservative force is gravity. And again, the energy effects due to weight and spring forces are conserved. So spring force is another conservative force. That means the energy gets traded back and forth between kinetic and potential without any losses. Okay, so and I will explain what that means on the figure. These type of forces are called conservative forces. So the examples for this one is weight force and spring force. So what happens here? So what we're going to do is we're going to start this point A on this corner and we're going to go counterclockwise. A to B, B to C, C to D, and from D to A, and we're going to complete the loop that way. So there's the box. Okay, so what we are doing is we want to know in every time we are going from from one line A to B, for example, what is the work done by the weight force? So when you go from A to B, you are going this direction. That is your D, and the weight force is going down. The angle between them is 90 degrees. What is the work done? Cosine 90 gives you 0, right? So that's why from A to B, the work done is 0. And then you're going from B to C. So that means you're really going upward. So that is your D in this case. But your weight force is downward. The angle between them is 180 degrees. What is cosine 180? Minus 1. And the force is, so I'm using F d cosine theta. F is mg, d is h in this case from B to C, and cosine theta is minus 1. That means this is going to give you negative mgh, right? And now if we do the same thing for C to D, again, since I'm going C to D, this is my displacement direction. And look at the weight force. There, the angle between them is 90 degrees. Cosine 90 in this equation will give you 0. So there's no work done from going from C to D. And D to A, you're going downward. That is your displacement. Mg is also downward. So the angle between them is 0. Cosine 0 is going to give you positive 1. F is mg, d is h because you're taking the same height. And the work term is going to be positive mgh. What is the total? When you complete the loop, and it's path independent really, but this is nice when we make a nice rectangle, like you can see it nicely, the symmetric case. But when you add up all those weight forces, the work done by the weight force, what you get is simply there's 0 and then negative mgh and positive mgh. You're getting 0, right? That's what means by without any losses, okay? It doesn't do work when you go through a complete loop. So that is why gravity is one of the examples that is conservative, okay? And that is the reason we can associate that with a potential energy. So that's why we have two choices. We can either keep it as delta U, change in potential energy on the left side on the energy conservation, or keep it as work done by the weight force on the right side. But one or the other, please be very careful and with that, and this is the reason why. And spring force is another case, right? So if we go back here, spring force is also the conservative force. And that's the reason either you have work done by the spring force on the right side or change in elastic potential. Okay, that different than the gravitational potential, elastic potential in the form of 1/2 kx squared on the left side. Okay, so the next thing is the non-conservative forces, and here's an example of friction. And for this case, again, we're gonna lose some energy, and once energy is transferred in one direction, you cannot recover all the energy. Okay, that is the reason it is non-conservative, and this includes friction. If you can think of any, like drag, right, air resistance, those kind of things are non-conservative forces. So why is that? Because the work done by friction on a closed path is not zero. Let's investigate this. So in this case, the object is on the floor because again the friction occurs between the bottom of this crate, right, or the box, and the floor, but we are looking from a top view. So object is on the surface, on the ground. Again, we're starting from point A, go to point B. This is the displacement. And what is the friction direction? Friction opposes to the intended motion. Since the intended motion is to the right, friction is going to be to the left. What type of friction do we have? Object is in motion, right? And that's why it's going to be kinetic friction. And the angle between them here is 180. Once again, since friction is a constant force, we can use, I'm going to write it as Fk. D cosine theta. Cosine theta in this case is -1. D is given as D. And Fk, on the other hand, is coming from the second law, which on the axis which goes through the page, because you need the weight force and the normal force. In that case, you will get the weight force, normal force to be the weight force, and since Fk is mu kn, in this case it's going to be mu kmg, because again on the axis through this page, it will give you a normal force to be equal to the weight force. Okay, so if you put these together, Fk is mu k mg and times d and times cosine theta. Cosine 180 is -1. So what you're getting is from A to B, the work done by the friction is negative mu k mg d. Okay. And now we're going to go from B to C. So we're going upward. That is our displacement. Once again, friction is opposing to this. Again, the angle is 180. It's going to be negative, right? Work done will be negative because cosine 180 is -1. Fk is the same as we show here, and D is the same. So you're getting the same work done magnitude as before because the distance is also the same. And from C to D, this is the displacement direction, and friction again is opposing to it. Once again, same friction, angle is also same, 180, you're getting the same work. From D to A, one last step to complete the loop. D is down, opposing force, friction is upward in this case, but it's really along the surface. The angle is again 180 degrees. And what you see is we're getting the same work function, work equation. So when you add them up, do you get 0? you do not get 0, right? So the total work in this case will be, I'm gonna write it here, 4 times, and there's negative sign, mu k mgd, for example. It's not 0. Okay, that is the reason it is a non-conservative force. And any forces like this will be counted as non-conservative force, and they are not associated with a change in potential energy. For example, friction will be associated with, instead of work done by friction, we are going to associate that with change in internal energy. Because when there's friction, if you put your 2 hands and then kind of kind of rub it against each other, then you're gonna feel like it is warming up, right? So you're really creating heat, and again, temperature change is related to the internal energy, right? Change in internal energy. So those are the things that will be done in this chapter, and we will see more examples of that. I hope conservative and non-conservative forces are clear, and hopefully that also gives you idea why we can associate some of the forces with the change in potential energy, but not all of them. Only the conservative forces can be associated with the change in potential energy, okay? And the work done by them can be associated with those.